Have you ever looked at a blurry image and thought, that looks weird? You know, where it almost has these strange, ghostly waves running through it? Well, today we're going to solve that exact visual mystery. We're going to find the ghost in the filter.
Okay, check this out. On the left, we've got a perfectly sharp, clean image. On the right, all we did was apply a simple blur. But instead of looking smooth, it's covered in these ugly, rippling artifacts. So what in the world is going on here?
You might think this is some kind of bug or glitch, but it's not. It's actually a totally predictable side effect. It's a clue, and it points directly to a very specific and very common type of filter that a lot of us use without even thinking about it.
To really get to the bottom of this, we can't just look at the image the way we normally do, as a grid of pixels. We have to peer into its secret identity, into a kind of hidden dimension that every image has.
And that hidden world? It's called the frequency domain, and this right here is the key that's going to unlock this whole mystery for us.
So here's the deal. Every image kind of exists in two worlds at once. There's the spatial domain, which is just a fancy way of saying the picture you actually see, the grid of pixels, but then there's the frequency domain. Think of this like the image's recipe. It's a mix of ingredients. Low frequencies are the big, smooth blobs of color, and high frequencies are all the sharp details and tiny edges.
And here's the really cool part. These two worlds are connected. There's this bit of mathematical magic called the Fourier Transform that links them. So any move you make in one world, like applying a filter to your pixels, has a corresponding and often very different looking effect in the other. They're just two sides of the very same coin.
All right, it's time to meet our main suspects in this case. A very simple filter and its very strange-looking secret identity.
This is a box filter. I mean, it's about as simple as it gets. It just takes a square region of pixels and averages them out, treating every single one inside that box is equally important. It's simple, it's intuitive, and its edges are perfectly sharp, abrupt. But what happens when we use that Fourier transform to see the box filter's secret identity? Well, it transforms into this shape, which is called the sinc function. And you can probably see the problem right away, can't you? It's got that big peak in the middle, but then it's followed by these endless, decaying ripples that just keep going. This sinc function, and yeah, for you math folks, it's just sine of x divided by x, this is our ghost in the machine. That rippling, oscillating nature is the direct cause, the smoking gun, for all those ugly artifacts we saw at the beginning. And, the source material for this explainer actually made a promise, saying they'd get formal about this stuff when they got to Fourier analysis. Well, guess what? We're here. Promise kept. Now we get to connect all the dots.
So, let's put it all together. How in the world do the mathematical ripples of a function in one domain create actual, physical ripples in our picture? Let's flip our thinking for a second. Instead of blurring the image by averaging pixels, what if we tried to blur it by messing with its frequencies? A pretty intuitive way to do that would be to just chop off all the high frequencies, right? Get rid of the sharp details. Well, doing that is the exact same thing as applying a sharp, box-shaped filter in the frequency domain. You're basically telling the image, keep the low frequencies, throw away everything else.
So here's the punchline. It all comes down to this beautiful, and in this case terrible, symmetry. Just as a box in the pixel world becomes a sinc in the frequency world, a box in the frequency world becomes a sinc right back in the pixel world. It goes both ways.
And this slide just lays it all out. By making that sharp cut in the frequency domain, you are effectively stamping the image with that rippling sinc function. The function's mathematical ripples become literal, visible ringing artifacts all over your final picture. And that's where the ghost comes from. Okay, so if the sharp-edged box filter is our villain, who's the hero? How do we get a nice clean blur?
Meet the Gaussian filter. Instead of a sharp box, it's a nice smooth bell curve. No abrupt edges. And here's its superpower. Its secret identity in the frequency domain is just another smooth Gaussian. No sharp cutoffs, and therefore no ripples are created.
I mean, the proof is right there in the picture. On the left, you get the ugly ringing from the box filter. On the right, you get a beautiful, smooth blur from the Gaussian filter. The difference is just night and day.
So the big takeaway here is really simple. Anytime you use a sharp, abrupt change in one domain, doesn't matter if it's on the pixels or on the frequencies, you're gonna create those ghostly, unwanted ripples in the other domain. When it comes to clean filtering, smoothness is your absolute best friend.
And you know, this whole idea isn't just for blurring photos. It shows up in audio processing, data compression, all sorts of places. Which leaves us with a pretty fascinating question to chew on. The sinc function is a ghost created by sharp digital edges. So, where else in our digital world might these ghosts be hiding in plain sight?